Good morning, everyone. I am Meysan, a PhD student of Professor Kota, and the title of my thesis is about hydrophobic surfaces and ice-phobic ones as well. And today I will talk about a part of my PhD thesis that I fabricated some hydrophobic surfaces, and I will represent some theories and techniques about how to measure hydrophobicity of surfaces. There are some lessons that we've learned from the nature, and they are naturally hydrophobic surfaces. The most famous one is lotus leaf, that is, as the Professor Manish expressed yesterday, it's the symbol of cleanliness because it's totally hydrophobic, and any kind of dust that sticks on it will be rubbed off by water particles, like when it's raining. Another example is some insects that we have in the nature, and we know that they are able to fly while raining, and they are able to run on the water without being sink. The reason is in their feet that they possess some tiny hair-likes, and these hairs are also have much more smaller pores, nano scale, that you can see in figure B. And the whole result is that they are not being wet, and not being wet means that they can be able to walk on air without being sink. And the things that now scientists are using is the hydrophobic properties of surfaces to solve their problems in industry. A famous problem in industry is corrosion of metals in contact with water. And it's been studied that they prove that hydrophobic surfaces can prevent metals from being corroded because they make air gap between the metallic body and the aqueous solution. So the process of the solution of metallic atoms in the water is being blocked, and it means that the corrosion speed will reduce a lot. And in this study, we can see that a normal copper plate was corroded 100 times more rapidly than a copper plate that was covered by a super hydrophobic surface. Another example that might be interesting for you mechanical engineers is about drag force that is dominant when we are a solid surface with contact in a moving liquid. As we know, normally we propose that the liquid layer in direct contact with solid surface is kind of stuck on it, and we propose the speed profile of the liquid that is passing through the channel, or a ship that is crossing the sea. But imagine we do something like this. We make a hydrophobic surface that doesn't make the water become stuck on the liquid. So the profile will start from here. The profile will start from here. And this means that the liquid will pass much more simply and with less energy loss in a pipe, or for example, a ship can cross the sea with less energy, and the engine can burn less fuel. And another use of hydrophobic surfaces that we are interested in this conference is about aeronautic. They studied that parts of the airplane that are covered with hydrophobic surfaces are shown less likely to being ice accretion phenomenon. And in this picture, this is a wind tunnel, kind of the same dimensions that we have right now. And the researcher put small wing and covered it with a hydrophobic surface, and they realized that less ice would be attached to it. And that's the subject that we are studying in my PhD thesis. And there are some basics about understanding the behavior of superhydrophobic surfaces and study their wettability with water. A more common way is to put a drop of water on it and measure its contact angle with water, that we can extract surface energy, or we have compare wettability of two different surfaces. And another one is when we have a dynamic state. This means that we have water or water drop moving on the surface, but it should be hydrophobic. So we have two different angles. The angles that is in front of the moving droplet, and another angle in the back of it. And the difference between these two angles are so important, and it's called hysteresis angle. And more hydrophobic surfaces have less hysteresis angles. And as Professor Manish had mentioned, if you pick a smooth surface of a super hydrophobic material, and you cannot reach to a contact angle more than 120. So the things that we are doing is to roughen the surface, because it's proof that roughened surfaces can increase the wettability of the hydrophobic materials. And there are two concepts about how to make the surface hydrophobic. The first concept is the material itself. So you should take the most hydrophobic material that exists. The other is putting roughness or roughening the surface. So, and these roughnesses can be classified in nano roughness and micro. And the best approach is to mix all of them together. Have a super hydrophobic material, roughen it in two categories. Micro and nano roughnesses. And there are some models to study roughened hydrophobic surfaces. And the Wenzel's model believes that the water enters into cavities of the roughened surface. And another believes that Casey state believes that the water become at the top of these roughnesses. And there are two formula to predict the states that predominates. We have we do a test with the roughened surface, and we do these two models to predict the angle, and which angle that is more closer to practical one is considered as the predominant state of the drop. Casey, that water not enters into cavities, and or Wenzel, that water enters. This part of thesis and that we are trying to develop is a fully roughened surface covered with a super hydrophobic material, I mean Teflon. Here we have a chemically attacked aluminum plate. I mean, we have a normal aluminum plate. We put it into highly corrosive conditions. And the things that happens is this chemical attack makes some roughness on the surface of the aluminum plate. And we have two different roughnesses here. In a microscopic approach, we have some micro hills that are covering the surface, and each micro hill, here is more magnification. Each micro hill consists of tiny particles in a nano scale that covers it. So we have kind of reaching to the approach that we have to have micro and nano roughnesses together. And now that we have a roughened surface, we try to deposit hydrophobic material. Here we use Teflon. And because of chemically inert properties of Teflon, it's difficult to deposit it on any kind of materials. So we use it physical deposition techniques called radio frequency plasma sputtering. The physics of plasma sputtering is based on here in the right picture, based on the fact that when you have electrical field, electrons can and an inert gas in this electrical field, electrons from this electrical field can hit to an inert gas. This inert gas can release two or more electrons and finally becomes charged. And since it's still in an electrical field, becomes to accelerate. And after being fully accelerated, since the electrical field is oriented to our target, here Teflon material, it will hit into it. And this energy of impact energy can be released by ejection of an atom of a molecule of our target. Excuse me. This process will continue until we have a cloud of flying particles or atoms. We have a cloud of particles of atoms flying from our target. And we are supposed to, these flying particles, reach to our substrate that we are trying to deposit material on it. In the left picture, we have an installation of a plasma sputtering machine. We have electrical field. We have vacuum pump because normally the deposition should be done in highly low pressures. And the entrance of inert gas, we use argon gas here. And the substrate that we use, that just fabricated roughened surfaces. Here on top. And we use radio frequency because Teflon is insulating. So if we continue doing that, it will be charged. And being charged means that for an more argon cations, it would be difficult to hit it because there is a repulsion force between charged atoms. And here we study the time of deposition. I mean, we put the installation and give time to deposition occur. And it was observed that by increasing the deposition time here from 50 minutes to 2 hours, we can reach much more. We can reach to more contact angles. That it means when we continue deposition, a more fraction of the surface is being covered by Teflon. In this picture, we have two different substrates. The first one is a silicon that is totally smooth, and we covered Teflon on it. The other one that is kind of roughened, and maybe that can be observed here, is our highly attacked aluminum plate, also deposited with Teflon. And we can see that the same material Teflon as a coating demonstrate different contact angles here, and the reason is just for the roughness that we made here. And as conclusion, we proved that we could deposit Teflon layers, and roughening the base substrate can increase the contact angle up to 30, and our fabricated substrate samples showed highly superhydrophobicity, and I will show you a film after all of that. And as we there is a problem because we did some deposition, and before that we did some chemical attack. So we have a mixture of these processes. And what about durability of the surface we fabricated? I mean, after the time being attacked by corrosive materials, being in contact with other chemicals, does these chemicals alter the properties of our surface that we just fabricated? These topics that should be studied more. And in our case, we are studying with hydrophobicity. So our surface should be resist in long time contact with water. So we should study its durability and keeping its proper hydrophobicity in the pass of time. And since we studied just one method of roughening and just one single hydrophobic material to deposit, there are several other ways to do roughening, several other materials to show hydrophobicity. So in coming studies, we should try to mix all of them and find an optimized combination of a roughened surface and hydrophobic material. And the property of ice phobicity, that would be the thing that we will study with this tunnel that just inaugurated yesterday. Now, I'll try to show a movie, and I hope it works here. Here is the plate that we fabricated, and we try to wet it with water. And as you see, it's totally hydrophobic, and any water, any type of water can attach on it. As you can see, even the pencil became wet, but our surface is totally dry. And the next step would be studying its isphobicity. Any more questions?